So, hello everyone. My name is Jorge Brescia. I'm from DSG, Software Composition Group in Bern. And what I'm going to talk about today is reusable dynamic composable units of reuse. Right? So that's the philosophical name. Actually, what they are is kind of dynamic traits. And I'm going to go little by little explain the details, and then try to show a small demo of how they work. So the key point is reuse, and this is a very old problem, and maybe one of the first structures of reuse that we know widely used are mixins. So for instance, the mixin, this is an example. We have a rectangle, right? So this is a glass, my rectangle, and I have another glass rectangle. And then these are mixins, right? Which they have a special process string and a serialized one, each of them. So, and then what they are applied, it's somehow there's some kind of creation of a mixin, which is a composition of the application of the mixin in the hierarchy, in the linear hierarchy of these classes. Okay. The particular details of mixin is that they have this linear composition, right? So with the hierarchy, we apply them at different levels. So that's how we introduce them. So we introduce this new. They bring some behavioral implementation methods, particular methods in the hierarchy structure. And then there's another problem, which is single composition. So when we compose them, so we have to do it one at a time. Okay, you cannot bring them all together and put it on top of one. Okay, classes. And once it is composed, we cannot access the particular implementation of as a string of encode on my method. Right, so they are composed somehow. We cannot access separately what we have now. Okay? So these were some of the problems of mixins. The original implementation, there was no operators. Now we're going to see that traits, which originally was introduced in Self, the prototype-based language, and later maybe you know traits out of the implementation of Nathan and Charlie, which did the implementation of traits for small, which is very nice work. And basically, if we have to define traits, it's just we get a class which the behavior of the class is going to be the subclass, the behavior defines the subclass plus the state, plus the traits, the method defines the traits, plus some glue methods. These glue methods are basically traits that define particular methods that use another method, right? So those are the glue methods. They have to be there in order for the trait to work. So far, so good? Okay. The particularity of the trait is that it's a flattened composition. It's not applied in the hierarchy, which is applied to the last class, right? So we apply it there, and then it belongs to that class, the composition. And the other detail is that it's multiple composition. We get a bunch of traits, we compose them with some operations. That's the key point of traits brought in. Particular operations to compose different traits, and we can apply it to a particular class in a composable way. All right? Good. So let's discuss the problem. The problem that was... Yes.
Sorry, you contrasted traits with mixins.
Yes.
So mixins, you gave this example of the S-string method, and each one called the super, and that specified the order
Yes.
in which all the new components were added.
Yeah.
Now, I should know this, because traits are pretty well known, so I hope Andrew won't kill me, but how do traits let you solve that problem without specifying a linear order?
So when you compose them, you have to, there's going to be conflict, right? Because both of them, so you have to have these operations, which, for example, I'm going to explain the operation that it has, which are conceptualized in the traits ones, which you have to choose. Either you alias them, so you put them different names, and then you provide some method that use them in a different order, or use them both for one, right? So you can say as a string from one class and as a string from another class with different names, alias. And then in a new implementation, you just use one of them or both, in whatever way you want. Or you can remove one, right? So you can say when I compose them, I don't want this one from here.
So basically you need some additional manually supplied information to tell you how
that's right. So
evolve.
when you compose, you want to have some compositional operations that are going to help you to produce meaningful composition.
That's enough for me to go on. Thank you.
Yeah. That's good. So Moose, most of you know it, it's a tool for analyzing data and software systems, right? And this particular example in Moose, when we analyze software, right? And we analyze software from different languages, right? So, for example, we have a meta model which is called Famix, okay, which just models the classes, objects, methods of a particular piece of software, right? So I bring this piece of software, I transform it, I bring it, I read it, and produce this meta model, which I use, or Moose use it, to do all his analysis, okay? That means that we have to have different implementations of the family class for different languages. So we have implementation for Java, we have implementation for Small, we have implementation for C, and as we go on, we have all these different explosions of different implementations, which some features are shared, but some other features are not. So we have this explosion. So how can we avoid it? Okay, so that's one problem, right? So we have this test class, which is not the same. If a test class in Java is one thing, so we inherit this from test case, the Java test case, and in Smalltalk could be another thing, right? Particularly, in Smalltalk it's going to be inheriting from test case class of Smalltalk. The other thing is that we have J2E. We know that sometimes we have annotations, right? So it's not inheriting from anything. So we have all these different things. So the question is, how can we avoid this explosion of classes? So what about objects, right? So we are talking about classes. Up to this point, we have been talking about classes. So mixing we apply on classes, objects we apply on classes, traits we apply on classes. So what about objects? What if we grab an object, right, and we give them some talents. We assign some talents, right? So we change them. We add the specific behavior that we need, or we modify the specific behavior that we need, in order to have a dynamic representation of the model that we need. So we are going to bring this Famix model now. We apply some changes to be a particular, so it has the basic implementation, which is okay. We apply some talents to the different classes of the model, and then when we apply some talents to the different objects of the model, the instances of the model. And then what we get is a runtime representation with a specific behavior that we need, that we can analyze it through the different tools of Moose and get a different behavior, and a different representation, a different graphs, and so on. Once we don't need it anymore, we throw it away. And in that way, we can not only have just J2E or Java or Moose different models, we can have the same a Java model which has specific things for analyzing dependencies, and a Java model that has specific things for analyzing system complexity. That's really useful, right? So we can dynamically change the implementation in order to move into different analysis. So we don't have to have an explosion of methods and classes, because everything is really hard to understand. We can control them and then reuse them. We can have these standards, and every time we need to have a particular model for a particular analysis, we apply these standards, we use it, and we throw it away if we want to. Okay? That's what talents is. And in the case of this particular problem, we're going to define a J2E class talent. It's an object, okay? Which just this one provides an implementation of is testing class. Okay? So when we apply it to a family class, the family class is going to be evolved. This is an instance, right? It's an instance which is called family class. It's going to be evolved to have that particular behavior is tested. So we're going to receive the message and it's going to delegate to the data, right? And then the data will implement something that's not defined in the class. Is that okay? Good. So what are the operations that we have? So we can define a method. So that's one of the most important things. So in the case of the JE class type, we say define is test place, performing, and this is the code, right? We can exclude the method. So maybe in a particular model we don't want to have a method because it doesn't, from a modeling point of view, it shouldn't be there, so we can remove two. This is pretty cool if you want to have immutable objects. So you have some auditing from you're in a bank, you have a banking system with all the accounts, auditing system, you want to know all the accounts, and you don't want them to touch anything. So you grab all your objects with all the accounts and everything, you just apply a particular talent that just removes all the accessors, and you give that model to them, to analyze. So it's kind of a security feature. Okay?
Can you not then apply another trait which adds the accesses back?
They can apply the trait that the accessors.
Well, you have a trait which removes, a talent, sorry.
Yeah.
A talent which removes the accesses.
Yes.
So there's nothing to stop you from applying another talent which adds accesses back.
Absolutely. There are some details that you have to be careful. You can apply a talent to the part of the system that adds talents, and then you create a system that doesn't allow you to do it. That's a closer thing, of course. Okay, so for excluding, we just say exclude this method. And then we can replace the method. So we say replace this. So there are two different things. One is adding a method, and the other thing is explicitly saying that if I want to replace this method. So there are two different things. So sometimes we want to make a distinction because if we want to apply to a talent that added the method and the method's already there, maybe we want to know that there's there. Okay. And then we have the composition operators. These are these operators that allows us to have a more rich composition. We have composition, which is, so if we want to have a particular family instance of family class which has Java class talent plus JQuery class talent. So that's going to have all the methods defined in a Java talent and a JQuery talent we want to have in this particular model. So we can start composing these models to have more rich models to apply different kind of analysis in. We can have aliases, which are written like I'm composing the Java class talent with JQuery class talents, but since I know that both of them define the EastS class, I think there's going to be a conflict. So I just alias it to a new method, to a new name. And I can refer to it in the code of other methods like that. Okay? Good. And the last thing is I can exclude a particular method defined in a talent. Okay, one thing is excluding from a class, another thing is from an object, another thing is excluding from a talent. Okay? Alright, so this. How much time do you have?
2 minutes.
Okay, that's good. Okay, let's go fast. Most of you have taken the Bifrost presentation? Okay, alright, go on. Alright, so Bifrost is a reflection system. It's very simple. The idea is, okay, so we have organized the method level in a new way, and we have explicit meta objects. So it's very simple. We grab an object, and what we express by attaching a meta object is how the object should evolve or change. Whether it has to change structurally, which is talents, or whether it has to change behaviorally, which is something else that is not here in talents. Okay? So this is talented object. But the important part is that this very simple mechanism can build really complex environments, right? So that's what we kind of saw in the tool. And two things are really important, I think. One is flattening. In traits, you have flattening, right? So you apply a trait to a class, and you can flatten the trait, right? So one thing is applying the trait to a class, and then all this composition you can flatten into the class. So then it belongs to a class, not to the traits, right? So you have a new class. In talents, what it's cool is that you can have two types of flattening. One is you grab an object from a class, and then you apply talents to it. And up to the point you decide, okay, this object doesn't belong to this class anymore, right? So all these methods I have added to it just make me realize that this is a new class. So I flatten it, so I detach it from the class and create a new class for it. So I create a new hierarchy for it. I understood that it's a new thing. This is very similar to prototypes. The other way is I grab an object from a class, I attach talents, and I realize that the talents that I attach should be applied to all the instances because it should be a normal behavior of the class. So I flatten it to the class. So I add the definition of the methods in this object. And the other thing, which is important, is the scope. Something that's really cool nowadays we do we do a lot of dependency injection, is that talents allow us to have scopes. So maybe if I'm running a test, and inside the test, I want to mock the database, right? For example, I don't want to hit the real database. I want just to say, look, in this context, in this scope, which is test, I want these talents to be applied to these objects. So every time that the object execution goes into this scope, the talents are going to be applied, all the tests are going to run, and then when they are done, the talents are removed. And as the objects move to different contexts and scopes, they apply and de-apply different objects, which is really cool actually. It's a nice idea. Okay, sorry about the demo. I have a full demo with the browser. There's a Glamour browser to show, but yeah, another time.
The URL is wrong.
Yeah. That's a good one.
Just delete the www dot.
Yeah.
Can you show us the browser?
Yeah.
Thanks.
Can you see that? All right. So these are not real packages, right? So it's just a way of having the objects. These are the talents, different talents, and you have different colors here. I don't know if you can see it. That's a yellow color. And for instance, there's a green one. What does it mean? So as I said, there are three operations. The green is add method, just to show there's an add method. The yellow, it's replace, so I replace it for another code. And the red, which is not here, is remove, right? So I don't want this message here. Okay? And maybe I can quickly run this thing. Okay, so you know that, right? Mm-hmm. Good. So I get one morph there. You follow me, right? Mm-hmm. I get one morph there, one of the many that are running there. And here there's a registry of talents. I get the immune atom. I get it there. And then I apply this particular talent, which is called immune, to the one particular atom in the graph. Right? So I apply it, nothing happened, so it readapted something, and then I start the infection. Can you see the guilty? Good. So that's the idea, right? So there's one guy, and what I did was just to say, if we look at immune atom, infected, just infected doesn't matter if it's true or false, we always put blue, right? So the guy is immune. When I just proceed, the guy is no more. Okay? Right, then we can apply another talent, which is green atom, and so on. Okay? I don't want to steal any more time. The cool part is this is only for creating, so I can remove, so I can come here and say remove, boom, I can define new things, right? New atom, new talent. Okay, so I have a new talent, I can define things. Okay, but the problem is that this is only for creating the structure of the talent. The question is how a browser for composing them, right, with all these operations would look like. Instead of writing, you see the code, we have to write the code, that's really ugly. The question is, how do we provide a browser that can compose them? We can really make it kind of really dynamic, the composition.
Clap again.